Okay, so yesterday we began our weeks-long journey here in circular motion. One of my favorite things to talk about. It's got a lot of practical applications. Today we're going to talk a little bit about driving, and especially since there's a winter storm coming. So there's lots of different stuff as usual, right? There's lots of different layers that we can get with respect to this. But more so than most other units, we can break it down into these four main ideas, right? So as we proceed through the week, if you can focus yourself on these four main ideas, and then understand the variance of all the different stuff that we're doing, well, just bringing them all back to this, then you're in business, right? So like our four main things are for us to understand how to use this sum of the forces equals mv squared over r, right? And, again, like usual, it's a little bit more complicated than just that. So today we're going to add on to a couple of those things. Can we understand our three, our three vectors, right? The velocity vector of anything that's moving in circular motion is tangent to the circle because the object always wants to go straight. Forces, if the object's going to be in a circle, forces will prevent this straight velocity by pulling perpendicular to the velocity towards the center of the circle to keep the object in the circle. And that gives cause to a centripetal acceleration that is directed towards the center of the circle and equal to v squared over r, which is really this part right here. So that this thing is really just a version of sum of the forces equals m times a. Right? Now, there are lots of different situations and lots of different circumstances where this circular motion stuff applies, right? So, the first of which, we talked about yesterday, right? If I am twirling this, if I'm twirling this ball, I look like Rachel doing this, right? I should be an expert, for goodness sakes, right? So if I'm twirling this ball like this, essentially, this is a freeze frame of me twirling this ball, all right? So as I twirl this ball, what forces are acting on the ball? Give me a force that's acting on this ball. Sammy.
The force of tension from the string.
The force of tension from the string is pulling where?
Pulling inward.
Yeah, radially inward. That's a word we're going to start using today a little bit, this idea of radially inward. Obviously, the idea of radial comes from the radius. All right? Radial means in the plane of the radius of the circle. That's going to be important for us here today. Any other forces acting on this thing? Lauren?
Gravity.
Yeah, gravity. Where's that pull?
Downward.
Yeah, straight downwards, right? So now, sometimes it's difficult for us to keep those planes in perspective. Ultimately, we're going to get to a particular screenshot up here where it's going to be easy, right? But in reality, sometimes the two-dimensionality of the board makes it difficult for us to draw these things, appropriately. So, in reality here, the forces acting on this wiffle ball are radially inward, which is towards your left, and then straight down for this weight. Now, technically, there's some technicalities that make that impossible, but for now, we're going to overlook those things. If I draw this as the force of tension acting inwards, right, and I draw this as the weight going down, you can see where the three-dimensionality of the board or the two-dimensionality of the board makes this an issue, right? Because what angle actually exists between the tension in this string and the weight vector? 90 degrees. Does that look like 90 degrees up there on the board? No, it doesn't. So in some cases, it becomes difficult for us to show appropriately how these vectors are drawn. All right, we're going to get to a situation with a car a little bit later on where it makes it easier for us to illustrate that. Right? Now, we also talked about the idea of a hockey stick exerting forces to keep objects. Right? So basically, what I've done up there is freeze frame that. So if I take this hockey stick right here, basically, like what we got, we've got a picture that looks, similar to this. Yesterday I was on the table moving a golf ball around in a circle. Now, if this stick is moving this hockey puck around in a circle, the circle, like the path for this hockey puck, could be like that. Could it be like that? So if I call this path 1 and I call this path 2, which of those paths could the hockey puck take? Could it take path 1? Could it take path 2? Could it take both of them? Or could it take neither of them? Which of those paths, based on where that hockey stick is, could the hockey puck take? Sam W.
It could only take one.
It could only take path 1. It couldn't take path 2. How come it could only take path 1 and it couldn't take path 2?
In order for it to be a circle, it needs to be pushed inward, but it's facing the opposite direction to be pushing outward.
Yeah, the hockey stick has to push the puck inward. So if the hockey stick is in this direction, it's got to be on the outside of the stick. It's got to be pushing inwards towards the center. So again, if we're drawing the force diagram of the forces acting on this puck, then I've got a stick force going this way, and I've got a weight force going that way. Ooh, what's wrong with this diagram? What's wrong with that diagram? There's a couple things wrong with that diagram. What do I got to change about that diagram, or what's wrong? What's different? Sam P. It's 2D, right? What angle should there be between these two things?
90.
Should be 90-degree angle. Is there a 90-degree angle up here on the board? No. I'm also missing a force. What force am I missing? The normal force, right? The normal force is acting up this way, right? Now think about that, right? Right now, the puck's got the weight and the normal force acting on it. Are those two forces acting to keep the puck moving in a circle? No, the puck's not moving in a circle, first off, right? But even if I take this stick and I move the puck in a little bit of a circle, and again, tough for you to see. Yesterday it was easy when I stood on the table. If I'm moving this puck in the circle, right, on the normal force and the weight moving the puck in the circle, are they keeping the puck in the circle? What's keeping the puck in the circle? The hockey stick is keeping the puck in the circle. So there's our first clarification of this little setup here. The sum of the forces radially equals mv squared over r. Only forces in the radial plane contribute to keeping the object in the circle. Now that might seem weird, but really it's just a variation of stuff we've already done. In other words, look, if I've got this hockey puck right here, if I want to accelerate the hockey puck, I can accelerate the hockey puck across the desk. Do the weight and the normal force have anything to do with that acceleration? No. I'm accelerating this in the x plane. So my y forces don't have anything to do with the acceleration. The acceleration comes from my hand, and then the acceleration as it's going across the thing here comes from the idea of friction. But the vertical forces don't have anything to do with the acceleration. So it really shouldn't be that big of a deal for us to understand that these things do not contribute to this centripetal acceleration, which is directed towards the center of the circle, because these things are not directed towards the center of the circle. So only forces that are in the radial plane, either pushing towards the center of the circle to help objects stay in the circle, or pushing away from the center of the circle to inhibit or hurt objects from staying in the circle, are a factor in determining this circular motion. Now, basically, I went on, I got a second picture. Now, obviously, they're different sticks, but, the reason why I went out there is for you to understand, like, hey, if this puck were moving in one big circular path, you can see that to keep the puck in that circle, the stick would constantly have to be on the outside part of the puck, pushing inwards. There's the force of the stick. Pushing inwards, there's the force of the stick. Notice that's directed inwards. The direction of our net force has to be inwards. These two pictures do a little bit better job, right? Because, based on how I've got this circle drawn, because now it eliminates a little bit of that. There's my weight force, and there's my normal force. And this allows me a little bit of better opportunity to show that those two things are perpendicular to each other. And the normal force and the weight force don't have anything to do with keeping that puck in the circle, even though that's kind of a bad-looking circle. All right? Now, that being said, this stuff applies to any type of curve. It doesn't have to be a complete circle. In other words, look, if this field hockey player is trying to move the ball, right? If she's trying to move the ball in a circle, there's Jack. How are you, buddy?
Good, how are you?
I am excellent. I'm excellent. Make sure I change that attendance. Oh, you came from attendance? So I'm
Yeah.
good. All right. So if this field hockey player is trying to keep this ball in a circle again, it could be a tight little circle. It could be a big little circle. Or this field hockey player could just simply try to make the ball go in a slight curved path for a little bit. So anytime we talk about any of this stuff, it's any curved path. It doesn't have to be a complete circle. It's just easiest, perhaps, for us to demonstrate this idea of a full circle, because when I twirl this ball around, we can see that, and we can illustrate that. All right. Now, how many people drove to school today? Where's my drivers? Did you drive the Beamer? All right. Is everything good with it? You're going to drive the Beamer tomorrow when the snowstorm hits?
There's a snowstorm, maybe we won't have school tomorrow.
Well, we're going to have it tomorrow. When might we not have it? Thursday, we might not have it. All right. I don't want to get your hopes up, right? So look at it. All right. Driving your car is an excellent illustration of circular motion and how it works. So if we imagine this car traveling around in a circle. So this car is traveling around this circular path. And here is a view, if there's a little camera person, like if there's Josh right behind here, he's taking taking a picture right behind the car, right? So here's my rear view right here. What forces are acting on this car as it goes around in the circle? Friction. All right. What direction is friction acting?
Wouldn't it like depend on would it just be going inward?
Yeah, friction is actually the force that keeps this car in the circle. Friction is actually the force that provides the centripetal force to keep the car in the circle. Now, if the car were traveling straight and like put the brakes on and skidded, then friction would act back against it, right? But in this particular case, it's friction's job to keep the car in the circle. What other forces are acting on this car in this particular situation? Right, read.
Weight and normal force.
Yeah, weight goes down, but normal force goes on. This is a great illustration though, right? Like this weight and normal force are not in the radial plane of the circle. But the friction force is directed in the radial plane of the circle. So the friction force is what keeps your car in the circle. And that's going to give us a really good opportunity right here to talk about how friction works to keep objects in the circle and how it changes this statement. Because I actually do not like this statement. We're going to get to that in a second, but first, Sammy, what do you got?
Is that why, like, if you're, like, drifting in a car, is that why, like, you, like, turn so well like that? Because if you have the brakes on, there's more friction. So just,
You turn well,
like, so,
you spin the car when you're
Yeah.
drifting. That's different, all right? So coming up in another month, right, we will talk about ideas of things spinning, right? So that's what your car is doing when you're talking about drifting. You are spinning on an axis that's through your body. That's different than turning the car in a curve around a point that is in the middle of that curve. In other words, like what's happening here? The car is moving its entire body around a pivot point that's in the center of that circle. What's happening when you're talking about is the car is rotating around an axis that's inside the car. So there's two different things. There's rotational motion and there's circular motion, which is what we are talking about. Circular motion is the entire object moving around an axis that's outside the object. We'll get to the rotational part of what you're talking about. All right? Now, let's use the car to address the problems with this statement. Because the equal sign actually isn't even the appropriate sign, right? The better sign would be to put the sum of the forces acting radially, right, and put this sign in the middle, right? The equal sign I don't like. This is a way better indication of what's happening. What's that sign? What's that mathematical symbol mean? You haven't come across that yet in your math class? Read what math you take.
Calc BC.
Calc BC. Mrs. Covington hasn't got to that yet? Anybody in UB math in here? No? Jack, what do you take?
Pre-count.
Pre-calc? You haven't got to that? And there's a reason why you haven't got to that, right? Because I just made it up. Right? Like that's a made up symbol. Right? And it's a made up symbol because I think it does a better job illustrating what's actually happening. This equal sign is misleading. Because the left side of this does not always have to be equal to the right side. Right? Now let's go over here to kind of illustrate that. Look, the sum of the forces radially equals mv squared over r. Well, again, man, I don't know that I really like that. What's providing the radial force here? The friction force is providing the radial centripetal force. The friction force is acting as a centripetal force. Now, those words unto themselves, right? Jack took physics last year. Anybody else take physics last year? Right? Like you're probably used to the centripetal force keeps objects in the circle. And the centripetal force is equal to mv squared over r. Well, that's not actually accurate, right? Friction force is acting as a centripetal force. Friction force is equal to mv squared over r, but I don't even like that. I like this symbol better, the one that I made up. Because if I could make up a symbol, I'd make this one up. And here's what it would mean, right? Right? In order to stay in the circle, those two things must be equal. So that symbol means must be equal in order to stay in the circle. Think about how different that is. What does this imply? This implies I've got some friction between the car and the road. It has to be equal to mv squared over r. That's factually incorrect. So this is misleading. What it really should say is that the friction force must be equal to mv squared over r in order for the object to stay in the circle. This eliminates the idea that friction force is always equal to mv squared over r. So be careful with that. Now, are we going to walk around drawing that symbol on our papers? No, right? You can't put that on the AP. But remember, there is the possibility that the friction force is less than mv squared over r. What happens if the friction force is less than mv squared over r? Sammy?
When it just goes the tangent line.
Yep. Right? You're going to drive in a snowstorm at some point during the winter. If you don't drive well, where do you end up? In the ditch, hitting a pole, off to the side of the road, right? There's going to be a lot of pressure on you now that you are hopefully a new driver. Your first day driving tomorrow by yourself could be in a snowstorm. All right? I want to talk to you about driver safety with respect to this. Look at it. The other reason I don't like this is this gives the impression that how fast you're going determines the friction force between you and the road. Or how big your turn radius is determines the friction force between you and the road. Right? Because, oh, by the way, right? So here's a turn with a particular radius. And here's a turn with a particular radius. Tighter turns have smaller turn radii. More gradual turns have a bigger turn radius. What determines v squared and r do not determine how much friction there is between this car and the road. What determines how much friction there is between this car and the road? Read.
The coefficient of friction in the normal force.
Boom. Look at it. Mu times the normal force equals mv squared over r. Do I like that equal sign, Laura?
No.
No. How come?
Because it's not going to be true all the time
It's not always going to be true. When's it going to be true?
when you're going in a circle.
If the object is actually moving in a circle. But let's think about this. So you drive in June, and that's way easier than driving tomorrow or today in the snow. Because what happens to you're driving the same car, so the mu doesn't change. I'm sorry, so the normal force doesn't change, but what does change? The mu. The coefficient for driving in snow is way less than the coefficient when the tires are touching the pavement in June, which means there's less friction available, right? So if the coefficient is down, therefore there is less friction force available. So if the left side of this is generally smaller, in order to stay in the circle, what do we got to do to the right side of this thing? We got to decrease the right side. In order to maintain this equal sign, I've got to decrease the right side. If there's less friction available, I got to decrease the right side. As you're driving, how do you decrease the right side? Sammy?
Well, either you can increase your turn radius or you can decrease your speed.
You drive like grandma. You take very gradual turns very slowly. Right? We like numbers. So let's put some numbers together. let's just say, I'm making these numbers up, right? Let's just say in June, mu times the normal force equals 1,000, which means you have 1,000 units to be mv squared over r. But in January, friction is less. You only have 700 units to keep you in the circle. Well, what do you got to do? Right? You've got to make a smaller v, or you've got to turn larger to make mv squared over r equal to 700. If it's not 700, if it's greater than 700, does your car make the turn you're attempting to get it to make? No. And where does it go? It goes where it wants to go. Where does it want to go? It wants to go straight line, right? Like, hey, we could do the same thing with this ball, right? So what's providing the force that's keeping this ball in the circle? Tension force, right? Is there unlimited tension that the string can provide? What happens if the string is under too much tension? It breaks. Isn't there a tensile strength for this string? Right? We got the pig hanging up right here. Isn't there a tensile strength for this string? Right? Like if I tried to hang from this string, it probably wouldn't work. The string would probably break, or the whole ceiling might come down. Right? But the pig is okay. Everything has a certain limit to it. So as I go to do this, right? It's the tension that is providing the force to keep the object in the circle. But will the object always stay in the circle? Not if the tension in the string gets too big. Now, what would have to happen for the tension needed in this string to increase? What happens if I get this thing going faster? Then I need more tension. What else would cause me to need more tension? What? If I was spinning a bowling ball around here, wouldn't that require more tension? It'd be way more dangerous. I don't want to do that. And Reed, what's the other thing?
Decrease the radius.
Yeah. Like, look at, I could put this under so much stress. If I went super fast, if I put a big heavy object on it, and or I put it in a smaller turn radius, to the point where this has a limit. The stuff on the left side generally has a limit. And if you exceed the limit, the object doesn't stay in the circle anymore. The object goes tangent to the circle. Now, there's lots of different ways that this can happen, right? And there's lots of different ways for us to deal with this idea of radial circles. Now, I'm going to keep this up over here, right? And I'm going to put this example out on Schoology so that you can follow along with respect to that. I'm going to keep this thing up because the next slide, I want it up there to compare. Right? Oh, did I put it on the homework?
Yeah.
Dang. Hopefully I at least switched the numbers.
No, you didn't.
Well, all right, consider it a bonus. Let's do it. Number 10. Anna, Sarah, and Trent are pushing a bowling ball, causing, so we're doing number 10, I guess, on the homework. That makes me mad. I'll switch the numbers here in a second
Don't do that.
for next year.
Yeah,
So the next year doesn't gain the same advantage.
And you get a bonus.
Hey, where's the bowling ball? Let me see the bowling ball.
It's okay.
Where is it? Oh, there it is. All right, so look. Anna, Sarah, and Trent are pushing bowling ball, causing the bowling ball to travel in a horizontal circle with a radius of 0.25 meters. Here's the bowling ball. Sarah, Trent, and Anna are pushing this ball, causing it to stay in a circle. Well, as soon as you see the word circle, how do we start this? Sum of the forces radially must equal what? mv squared over r. And how do we know that that equal sign is okay in this particular situation? Because the ball is actually moving in a circle. Now imagine this as the surface, right? Anna is pushing, oh, and let's just say, where's my hula hoop, right? Let's just say, whoa, that the ball is moving in a circle that can be illustrated by this hula hoop, right? That's a horizontal circle. So the bowling ball has, come on. There we go. The bowling ball has a weight that's acting downwards, and it's got a normal force that's acting upwards. Do either of those play a role in moving this ball around this circular path? No, Rachel, how come? It's not on the radial plane. But what's happening here? Sarah, Trent, and Anna, I think, are pushing in the radial plane. What's happening here? Anna pushes radially inwards. Sarah pushes radially outward, and Trent pushes radially inwards. If I'm drawing a diagram of that, here's the ball, here's the circle. You know, what's happening here? Sarah pushes radially outward, Anna pushes radially inward. There's FA, there's Anna's force, there's Sarah's force. Trent pushes radially inwards, F sub T, Trent's force. Who's helping that ball stay in the circle? God bless you. Who's helping that ball stay in the circle? Anna and Trent. Sarah is hurting the ball's chances of staying in the circle. Now, in order for the ball to stay in the circle, the sum of those forces must be directed inwards and be equal to mv squared over r. Carl, can you give me an expression for the sum of the forces acting radially?
FA plus FT minus FF.
Equals mv squared over r. I love that Carl made the inward forces as plus and the outward forces as minus. And I love that because our rule is anytime there's acceleration, we always want the forces to be in the positive direction. My bad. Anytime there's an acceleration, we want to designate the direction of the acceleration as positive. So any of those forces in the direction of the acceleration have to be positive. And which direction is an object traveling in a circle accelerating? Towards the center of the circle. So towards the center of the circle is going to be positive. Away from the center of the circle is going to be negative. All right. What's the question actually ask us for? Weight. Does weight appear up here? No. So that's our first problem. The thing that we don't have isn't in here. Like we've started this the exact same way we've started everything else. Now we do our problem solving the same way. We've got to work weight into this equation. How do I work weight into this equation? Sammy?
You can make it, you can make mass divided by 9, or wait, no. So if it's mass, like you can multiply it by 9.8, and then that's your weight.
Yes. So how do I get weight into here? If weight is equal to m times g, then what's m equal to? W divided by g times v squared divided by r. I haven't done anything to over here. Fa plus ft minus fs is equal to w over g times v squared over r. So we've solved our level 1 problem. Now, if we know everything else other than w, we're good to go, right? What's the value of fa? Anna pushes radially inward with a force of 8. Trent does what? 60. Sarah's force is 50. G is 9.8. What's the radius? 2.5. And V is? Do we know everything but the thing we're looking for? Now, how do we get the thing we're looking for by itself? We got to get rid of G and R. How do we get rid of G and R? multiply it. How do we get rid of v squared? Divide it. So g times r, parentheses, times fa plus ft minus fs divided by v squared is equal to the weight of the object. Do I know all of these things? Can I get a number from that? I could. Do I care about the number? No. Can we do that algebra? Can we understand what's going on in that particular situation? Do the forces acting radially add up to mv squared over r? More specifically, do the forces acting radially sum up to a net force directed inwards that is equal to mv squared over r? Lots of different things can provide those forces that are acting radially. Anna, Sarah, and Trent can. Strings can. Hockey sticks can. Field hockey sticks can. Feet can. Friction can. One other really big thing that in our particular course provides a centripetal force is what? Gravity. Right? Gravity can provide a centripetal force. So if I look at this particular situation right here, right? Gravity acts between any two objects, right? The bowling ball is gravitationally attracted to the hockey puck. The hockey puck is gravitationally attracted to the hula hoop. All of those things are gravitationally attracted. Isn't the spacecraft gravitationally attracted to the Earth? Right? Isn't there a force that is directly to the center of the Earth between that spaceship and the Earth? Yeah. Where does the spaceship want to go? Where does the spaceship want to go at any particular time? Straight. Spaceship wants to go straight. Gravity is providing a force towards the center to cause the spaceship to go in a circular path called an orbit. Right? Well, in order for the spaceship to stay in the circle, then the sum of the forces acting radially must equal mv squared over r. In the case of the car, friction provided that radial force. In the case of this bowling ball, the combination of Anna, Trent, and Sarah provided the centripetal force. In the case of this, what provides the centripetal force? Gravity. F of g equals mv squared over r. Oh yeah, I put it up here for you. Yeah. How do we calculate the gravitational attraction between the spaceship and the Earth? How do we calculate that? You've done it 15 times probably, if not more. We're just doing it in a different context. Let me rephrase that question. What determines how much gravitational force of attraction there is between the hockey puck and the bowling ball? Distance between the two? Masses of each one of those things? And what else? That gravitational constant, big G. I can calculate any gravitational force by using big G times the mass of the two objects. Now in this case, it's the mass of the Earth and the mass of the spaceship divided by the distance between those two things squared. Listen, the spaceship will eventually end up over here. It's already written on a diagram. Right? Like, look at it. This is the orbital radius right here. That's this. That's also the distance between the two objects. Equals mv squared over r. Now, mathematically, some interesting things happen in this particular situation. Most notably, right, one of these r's goes away. What else goes away? Look at the math here. What goes away?
The mass of the spaceship.
The mass of the spaceship. Now, that's a little bit weird, but when we really think about it, right, bigger objects require more force to stay in the circle. So if this spaceship were bigger, it would require more force. But it would invariably get more force because it's bigger, and bigger objects experience more gravitational force. So these M's cancel out, and one of the R's cancels out, and we're left with this expression, which often comes up for us. We don't want to memorize this expression. We want to understand this process to get to this expression. But can we think about what this is saying to us as far as orbits? Right? There's lots of stuff orbiting around. All right? The spaceship, the International Space Center is orbiting around the Earth. We have lots of satellites orbiting around the Earth. The Earth is orbiting around the sun. Now, that path is elliptical, but it's pretty darn close to circular. What is this telling us? What's this tell us? Carl, give it a whirl.
The velocity of the object around the Earth in this case depends on how far away you are from it.
There's only one combination of R's for every particular V. This and this are constants. So if an object orbiting the Earth has a particular velocity, it will orbit at a particular radius. Do the reverse. Right? If we want to put a satellite in a particular orbit, we have to launch it at a particular horizontal velocity and allow gravity to take a hold of it. There are lots of different things that provide this centripetal force, or that provide those forces that act centripetally is probably a better way to say it. Our ability to adapt our four main goals over there to those specific situations is really what we're after, just like everything, right? We've had lots of different circumstances that we have to make adaptations for. Can we do that now in the circular frame of reference?